Here let's continue to take a look at another example here. So for this example, we want to calculate the stress at the first one at point H here, okay? And so again, the step one is to define a coordinate system on the cross section containing point H. So here, this is a circular shaft. So here, this is a cross section which is circular. So that's the cross section here. And then we define the coordinate systems and say this is centroid here. So we define the longitudinal or axial direction as x, and here the h is on the north pole, so that's a y, and k is on the west side, and that is z. Okay, so for the first one we define the x, y, z coordinate systems and place the origin at the centroid. Then the next step is, based upon the given loading here, we want to know what is the reactions happening on the cross section here. So that cross section basically is here. Okay, so that section is this one here. So for this one, basically here is you need to apply what you learned from statics and about the translation of the force. And here in terms of the force component, and that can be easily translated P1 equal to 15, basically equal to F here, okay? So that is P1 in magnitude in the same directions. And P2 is 18, so basically that translated to here, that's a V, okay, that is 18. And sorry, this is P2. And now in terms of the couple, or components, basically here the two loadings applied at the same location A. So here let me take advantage of this formula. The bending moment equal to arms times cross product the F here. So here is the keys. So for example, from the point A, the first one you measure the location of point A, which measure from the coordinate system, which is at the at the centroid of the cross section. So for this distance, and that is called the R. Okay, so from here, in terms of our coordinate system x, y, z, the coordinate, this vector is simply equal to in x component that is 60, and in y direction is 0, and z direction is minus, so that 50, so minus 50 in the unit of the millimeter here. Okay, so that is R, so I put the R here. And what is F? And again, the F is the two force components applied the same location. In X component is minus 15, and the Y component is positive 18. Okay, so basically for this case, once you multiply together, that has a unit and kilonewton, something like this one here. Okay, so you conduct this one, then you can right away see the result will give you three components, and that is mx and my and mz, etc. Okay, so mx is the bending about the x-axis, and about the x-axis actually in terms of our physical the understanding, for this case that is t, so basically t equal to this component here. Okay, t equal to mx, and what we learned, we calculate mx, and that is the 900 kilonewton millimeters here. Okay, so that is this one. And then this is the my. My is the couple component about the y-axis, actually is this one. Okay, so that is the one we calculated 750 newton meter, and this is the mz, is this component here. Okay, and 1080 newton meter. So this page, this step one is you have to review. If you don't know this one very well, or you cannot do it very well, please review what you learned from statics. Okay, so the prerequisite of the ES3, this class, is the statics. So again, this is purely from statics. If you still confused on that one, then go back to review the statics. So that is step one. So step two is, once we have all the reaction components, including force components and couple components being calculated on the cross section we're interested, then we begin that we're going to exercise what we have learned from chapter 2, 3, 4, and 5, 6 for this kind of the determine the stress. Okay, so here let me tabulate. So here we have a force type, and we have the normal stress, and we have the strain stress. I like to tabulate because that will give us the very good concise view. And the first one, the loading type is V. So we know the normal stress in magnitude, this P over A. This is from our chapter 2 here. If you remember our chapter 2, we have this thing, this is P here, and then this cross section is A. The normal stress simply is P over A. Okay, so that is this one. And this is the magnitude, and for given this case, and that is compressive, so we put the minus sign per our sign convention, tension positive and compression negative. Due to axial loading, no shear stress, okay, 0. Now we move on to the second loading type. So we done this one, let me cross out this. Now we move on to V here. Okay, so V is the transverse loading. So transverse loading contributes nothing to normal stress here. And the shear stress, we know that is VQ over IT. This is the template here. Okay, so we see. So this is a cross section, and that is a cross section here is where the edge located. And now the V is pointing upward like this. And this is the centroid. So from here, you should right away to identify first. This is the neutral axis. Okay, so that is the neutral axis for this case, and I is the neutral axis. Actually, is our Z axis. Okay, so I is the moment of inertia respect to the IZ. So for example, if the radius is C, basically IZ equal to pi over 4 times C to the 4th power. And V is the given one we simply previously calculated. We can copy from the previous slides. Okay, so that should be no problem. And what is Q? Q, again, Q is the shaded area and above or below the cut. And here let me make one example. If say here, if we interested in say the point here, then we make a cut. Okay, and then that cut is to parallel the neutral axis, and then from that cut we pick the shaded area like this one for determining the Q. So from here, when we approach this point to H, okay, say if we raise the location of this point up until point H here, are you able to see in this case the shaded area equal to 0, that correspondingly Q equal to 0 for point H. Okay, so that is at point H here. Okay, so basically it's no bother to determine T. Basically this term, whole thing for particular point here is 0. Okay, and now we move on to the so we done this one. So now let me say work on the T. T is the torsions, and nothing can go to the normal stress, and this is a TR over J, that is our template. Okay, and then here this is the, let me draw the section. This is the section, and this is the center or centroid here. So now this is the T applied. Okay, we copy from this information here. So now again, here is where H located. So here we connect from H to the centers, and then from there we draw a tangent. We draw a tangent to H, and in the direction aligned to the circulation of T. So that gives us the torque, and here, okay, and what is R? So here the R is simply equal to the radius C here, okay, and J equal to pi over 2 C to the 4th power, and we are, I believe we are given C here. So for this case, I think when I copied this information, I forgot, but it's okay. We can see the solution later. Okay, so assuming we know the C here, okay, so we can formulate this one. So T is given, so T simply is being previously calculated. So basically this one is done. Okay, so this one is done. And now we look at the bending stress. So the bending stress, we have two. Let me work on the my first. Okay, so my is here. So let me draw the my. So this is the cross sections, and this is the y-axis, and this is the z-axis, and my is applied in these directions. Okay, so my is like this one. So from here, we first identify the neutral axis. Okay, so my here we have calculated the magnitude. Sorry, this is our template. Okay, so for this template, then we can determine m is our given moment is my, and I is the moment of inertia with respect to the neutral axis, and our neutral axis is the y-axis. So here is y. Okay, so I is I1. And what is y? So y again is the distance from the point to the neutral axis, and here is our h here. H is exactly located on the neutral axis. So for this case, if we want to determine the stress at point h, y equal to 0. So this one equal to 0. Okay, so now we can move on to mz. So now we done the my. Okay, now we do the mz. So let me do this one here. So this is the again y-axis and z-axis. Okay, so mz is applying in that sense. Okay, so let me just do the count here. Okay, so now h is here, and so if regarding to the bending mz, so this is our neutral axis. Okay, so mz again in terms of the template we have is my over I. That is a magnitude. Okay, and then let's first determine the magnitude. So m where that is given, that is our mz here, and I is a moment of inertia with respect to the neutral axis, and which is the z-axis for this case. So that is iz. Okay, and then what is y? Y is the distance measured from the point where is h to the neutral axis. So that is this distance, which actually is our radius, c. Okay, so that is the magnitude you determined. Then we can determine whether it's tension or compression. So from this case, you can see the upper portions that should be in compressions here, and in the lower portion should be in tension. So basically here this is a magnitude, and then here you need to add it up a minus sign because we identified this is compression. Okay, and then also for due to bending stress is contribute nothing to shrink stress, so that is 0 here. Okay, so now we add it up together. So now we apply the superposition principles. So basically we take the summations. So here we added up the two components. So the normal stress actually in x directions because the superposition principle here. Okay, we sum it. So that is the minus p over a and minus and n z and times radius and iz. Okay, so basically this one is this term here. Okay, and this one you plug in the numbers, then you should get the right answers, and definitely this is compressive. Okay, and you will get a negative sign, that's compressive. And then again we apply the superposition to the bending. Sorry, here I messed up to the bending stress here. 0 0 non-zero 0 0, so only have this one. So that is the bending stress equal to TR over J. Okay, and TR over J, and that is in x plane pointing to z direction here. Okay, so that is a one. And then let me release some space. I want to give you an important summaries of this calculation here. So here, let me say we pick up a small square around the edge, something like this one. Okay, that's a small patch kind of sitting on the top. So that small patch basically looking like this one to align to our directions. So here is the x directions and y direction and z directions. Okay, so that's alignment. So this small patch basically is here. Okay, and that is the h sitting here, and this is the parameters of the shaft, parameter of the sections. Okay, so hopefully you see what I'm doing here. Okay, so that's the parameters of the sections. Okay, so that's going here. So now we have determined the normal stress, which is negative. So this is sigma x, whatever we calculated here. Okay, and tau xz actually is pointing to, if you map the informations, if you map these informations to here, that is tau xz here. So again, if you complete the whole drawing, so this is the stress, and that would be like this one. Okay, so again, if you pick a small patch, I would say this is small stress element. Patch, and the small stress element patch is simply used to demonstrate the distributions and the directions of the stress. Okay, so if you have this one, then we can successfully and very clearly put our calculated result into here to indicate the directions of the components here. Okay, and this is a very concise and very clean, no, it's very clean, the calculations, and then given the magnitude and then the directions here. Okay, and here, sorry, I didn't give the C, but here I don't think that is important, and as long as you understand the whole details here. So that is for this example.